In the last video, I've obtained the formula for the energy of the orbit number n in terms of these quantities. And this allows us to finally calculate the energy of each orbit directly. So what I want to do here is to look at how we can use this formula to find this peak eventually. Okay. So what I want to do is this. I want to find the difference between the energies of these two orbits, orbit number 2 and orbit number 1. So what I need to do is to find E1 and E2 and then subtract them. So that's what I'm going to do. Let me just clear this off. Right. Okay. So what I want is to find E2 minus E1 because we think that it is the energy given out when an electron goes from this one orbit to the lower orbit 2 to orbit 1, that produces the X-ray photon that shows up in the X-ray spectrum. So in order to calculate this, all we need is to substitute. When for E2, we just need to substitute the 2 into the n there, E1 1 into the n there. So to make it easier, let me just rewrite this a little bit. Okay, so that there's a square there. Right. So the m there, from the z I have a z squared, the e squared I have a e to the power 4, 2 and the 2 squared there is gives an 8, epsilon naught squared and h squared, and the n there, I'll think about this as a separate times 1 over n squared because I'm going to use different n's. So this one, if I put n equals to 1 and n equals to 2 into there and try to subtract them, what I'll get is two terms with the same common factor. So I'm just going to write this out directly. M z squared E4 over 8 epsilon naught squared h squared. Okay, and when n is 2, when n is 2, right, there's a minus sign there. When n is 2, I have 1 over 2 squared. 1 over 2 squared minus. When n is 1, I have 1 over 1 squared. So this is what I have. And that is 1/4 minus 1. So that's minus 3/4. So therefore, we are saying that should be the photon frequency HF. So this thing here gives minus 3/4. Okay, so multiply by this, minus and minus cancel. Okay, we are going to get 3. I'm going to put z squared on one side for a reason that I will explain in a moment. M and E fourth, and then 8, that'll be 8 times 4, that's 32, epsilon naught squared h squared. Right, so what we have here is a formula. We have a formula for the photon energy in terms of Z, the number of protons, or the atomic number. And this is actually a really useful relation, because just by measuring the X-ray wavelength or frequency, you can actually use this to work out the number of photons, and therefore you can identify the element in a periodic table. So it's really useful. And what I'm going to do now is to think about plotting a graph. Okay, so if I want to plot a graph of this, what sort of graph would I plot? Let's see. Now I can, it's always convenient, if you're talking about measurements, to have a straight line graph. So in this case, it's a z squared. So, but to make it a straight line graph, I can either plot, say, HF against the energy against z squared, or I can plot the square root of energy against z. So this is what I'll do. I'm going to plot square root of the energy. Okay, plots against Z, the square root of HF. Right. Now if I do that, I would expect to get a straight line. Okay, I would expect to get a straight line, and let me make that a little bit more explicit. If I take the square root of this, then the square cancels. Okay, so then if I think about this as y, and I think about this as m, and I think about this as x, I get y equals to mx, which is the equation for a straight line. Okay, so that's why I would expect to get a straight line, and in fact, if I try and plot this, let me just draw what you would expect. You would expect a straight line from the origin to there. Okay. So that's fine. That's what we expect from all the assumptions that we made and all these calculations. But how does it agree with the measurement? These energies, or the wavelengths, are something that we could actually measure by looking at the X-ray spectrum for each element. So let's imagine the possible atomic numbers, like 1 for hydrogen, 2 for helium, 3 for lithium, 4, 5, 6, 7, and so on. So for each of these elements, suppose that the X-ray spectrum is measured. Now, hydrogen, helium, we'll skip the first two, because those first two only have one shell. We need electrons from another shell. Okay, don't worry about that. So anyway, I'll say roughly I'll start from there, Now, what was actually found when it was measured was points that look like this. Okay, and so on. So a very strange thing was observed when the graph for this equation, this calculated equation, was compared with the measured points. Okay, so that's calculated and these are measured. These are measured and that line there is calculated. Now what was found was that the line, the calculated line, is off from the is away from the measured points by exactly 1 unit to the left. So it's very strange, and it's like we are almost getting it. We are almost getting it. We get a straight line which is really close, but not quite. Right? We're not quite there yet. So why is it off by 1 unit?